Hello dear students, welcome you all. In this lecture, I am going to discuss about the distribution of n particles in two compartments, right? Distribution of n particles in two compartments, right? This is the case that we are going to discuss in this lecture, right? You know very well, we have discussed the case of distribution of four particles in a two compartment, right? We have discussed the different number of arrangements, I mean microstates, macrostates, right? Thermodynamic probability, all these things has been discussed in this case, distribution of four particle in a two compartment. Now we are going to extend this to the general case of n particles in two compartments, right? So before going into the distribution, we have to make some assumptions. The first assumption is here that these particles are distinguishable, right? First, we can distinguish these particles as these are classical particles, right? Second thing is there is no restriction on the number of particle entering in a compartment, right? The third one is the number of particles in two compartments is always equal to n. It means the number of particle in first compartment, but number of particle in second compartment, it should be equal to n. Clear? So this is the case, right? So we are going to discuss this case here. So for it, let's consider uh, two compartments of equal size, right? Like these are two compartments, identical compartments of same size. This is compartment 1. This is compartment 2, right? So we are going to distribute n particle in these two compartments, right? So the first thing is, first of all, we have to find the number of microstates, right? Microstates, right? Total number of arrangements. So we know in case of distribution of four particle in two compartments, the number of microstates were 16. Clear? 2 raised to power 4. So here, as we have n particle, so obviously the number of microstates will be 2 raised to power n. Clear? This is what? Number of microstates. Right. So this is the number of microstates. Right? Now, number of macrostates. Number of macrostates in this case was 5. Clear? So here the number of macrostates will be 5 means 4 plus 1. So here it will be n plus 1. Clear? So these are the sorry number of macrostates and microstates. These macrostates will be like you can take the examples 0, n, right? 1, n minus 1, comma 2, n minus 2, so on, right? N 0. So these are the different possibilities. Clear? Macrostates. These macrostate can be further having different arrangements which are called microstates. So total number of microstates will be this. Clear? And total number of macrostates this, right? Now, as we have the n particles, right? And the particle are distinguishable. So the total number of arrangements of these particles is equal to how much? N P N, right? This give us the total number of arrangement, permutation of N P N, right? So it give me n factorial divided by n minus n factorial. So it is obviously n factorial, right? Because n minus n factorial is equal to 0. So this n factorial is the total arrangement of these n particles, right? Now, these total arrangements include some meaningful arrangement as well as some meaningless arrangement. So, in actual, the total number of arrangements should be equal to number of meaningful arrangement into meaningless arrangement. Clear? So, now we have to calculate the meaningless arrangements in this case, right? So let's consider one possibility, right? In this possibility, the first compartment has a n1 particle and the second compartment has a n2 particle, right? Such that n1 plus n2 is equal to n, right? Now, these n1 particle, when they are present in the first compartment, for example, let's take we have four particle, right? A, B here and C, D here, right? N1 is AB, N2 is CD. Now, if I take it as BA, if I write it as DC, again it is the same thing. It is the same thing, right? It means the arrangement of these N1 particle among themselves is meaningless. Similarly, the arrangement of N2 particles among themselves is meaningless, right? So, arrangement of n1 particle among themselves means n1 factorial. Similarly, arrangement of n2 particle among themselves n2 factorial. So, the total number of meaningless arrangements should be obtained by multiplying these with each other, right? This give me the number of meaningless arrangement. Clear? Now, the total number of arrangement, as I have written here, it is equal to number of meaningful arrangement, number of meaningless arrangement. It means n factorial is equal to number of meaningful arrangement into n1 factorial into n2 factorial, right? So it give me number of meaningful arrangement, right? That is equal to n factorial divided by n1 factorial into n2 factorial, right? Number of meaningful arrangement, right? So this is what number of meaningful arrangements means. It is thermodynamic probability for the case n1, n2, right? So it is thermodynamic probability n factorial upon n1 factorial into n2 factorial. So this is the thermodynamic probability, right? Number of meaningful arrangements of this macro state, right? We have took the case of this n1 and n2. First of all, we write down the total number of macro states and micro states in case of n particle in two compartments. Then I write the total arrangement of n particle among themselves, right? Because these n particle can be arranged them among themselves. So it is given by n factorial. Number of meaningless arrangements are this. Then number of meaningful arrangement gives me this, which is thermodynamic probability. Right. Now we know the probability of a macro state n1 comma n2 is linked with the thermodynamic probability as it is equal to w n1 n2 upon 2 raised to power n. 2 raised to power n means total number of micro state, right? So this is the probability. We know the probability of a macro state is equal to thermodynamic probability multiplied by probability of a micro state. So probability of a micro state obviously 1 upon total number of micro states. So it give me n factorial upon n1 factorial into n2 factorial multiplied by 1 upon total number of microstates 2 raised to power n, right? So this is the expression for this probability of this macro state. Clear? Right. Now I can write in place of n1 and n2, I can consider that here there are r particle and here there are n minus r. Again the same thing. So in that case, it will become p r comma n minus r, that is equal to n factorial upon r factorial into n minus r factorial into 1 upon 2 raised to power n. Right. This is the uh, required expression for the probability of a macro state, right? When we are distributing n-distinguishable particles in two compartments of equal size, right? Now, from this expression, I can write down the expression for the probability of most probable macro state. Now, from this expression, it is clear that this entire term will be maximum when r is equal to n by 2, because you can see here this is r, this is n minus r. So this denominator will become minimum when this r is equal to n by 2. So if I put here r is equal to n by 2, then it will become n factorial divided by n by 2 factorial into n minus n by 2 means n by 2 factorial into 1 upon 2 raised to power n, means when there are 50-50 number of 50-50% number of particle in both the compartments. You also have seen that in the case of distribution of 4 particle in 2 compartment, the distribution 2-2 was having maximum probability. So again the same things comes out here, right? This distribution of n particle in 2 compartment, right, will have maximum probability when both the compartment will have a equal number of particles, that is n by 2 n by 2. So I can write it in this way, n factorial upon n by 2 factorial square into 1 upon 2 raised to power n, right? So this is p n by 2 comma n by 2, right? P maximum, I can say P maximum, because only then this will be maximum. This maximum means this denominator, this term is a minimum, right? Now I am coming to the minimum value of the probability, P minimum. So you look at here, this will become term will become minimum when we will have this term, because these two terms are multiplied with each other, right? So when r is equal to 0, you look at here, or we can say n minus r, means the entire number of particles, all particles are present in only one compartment, and the second compartment is fully empty, right? So that in that case, it will become r is equal to 0 means n factorial upon 0 factorial into n minus r means what? N factorial. Clear? Into 1 upon 2 raised to power and 0 factorial 1, right? So it give me 1 upon 2 raised to power n, right? So this is the minimum value of the probability. Obviously it will be because this factor cannot be altered. If we look at the this formula for the distribution, then from this formula it is clear that this factor cannot be altered, it is constant. We can alter this term only, right? So this value will become minimum when this entire value will become either 0 or 1. 0 means it will give probability 0, so that case is not considered. So minimum means when this term is 1. This term is 1 when this r is equal to 0 factorial, right? So r is equal to 0 factorial means r is equal to 0. All the particle are considered in a one compartment, right? So it give me the p minimum value. P minimum is equal to 1 upon 2 raised to power n, right? So now we have derived the expression for both maximum probability and minimum probability, right? P maximum is equal to this, right? And P minimum is equal to this, right? So this was the case of a distribution of n particle in a two compartment. There are many numerical problems based on this expression, right? And they are very simple, right? So you can do them quite easily if you know this formula, right? And you know P maxima and P minima formula also, right? So thank you very much.